Okay, good afternoon, everybody. I hope everything is well with you. I'm really sorry to bring you at this time of the day. However, if you want the review, you need to abide by my time, okay? So I hope that, yeah, before I start with the lecture, I would like to advise you with the rules here in at the review lecture. So basically, what you need to do is I'm gonna go over some questions now with you, exercises, and we will solve it together. At any time, if you have a questions, you can either use the chat or raise your hand. So I'm gonna give you like 2 minutes just to feel comfortable with Zoom, with the environment. Then after that, at the end of the lecture, what I'm gonna do is I'm gonna unmute all of you. So we'll make it a big discussion, okay? At any time, if you have a questions and you don't like typing, what you can do is raise your hand. You can either type on the chat, or if you do not type, I'm gonna unmute you so I can talk to you directly, okay? Yeah, one other thing is that I know some people, they hate Zoom, and I don't blame them because it's not that secure. So we're waiting until the Microsoft team is fully integrated with the Brightspace, and after that we will move all the review sessions to Microsoft team. Okay, because as you saw at the lab, the Adobe Connect sucks. Yeah, we'll have 3 more minutes. If you need to grab a coffee, go ahead. Nobody is preventing you. Yeah, for Quartz on Mac, you need to install the Microsoft remote desktop connection application. If that doesn't work, what you can do is you can install Parallel and install Windows, and from that you can either use the remote application from the university, or you can install Quartz on your machine, okay? I thank you, Karim. Parallel, VMware, anything. Any environment that enables the operating system virtualization. How can we get the email of our partner? Well, let me tell you something. I know it sucks that you cannot get the email. However, if your partner wants to join you, he can do whatever method to contact you. So Due to privacy issues, I will not be able to post all the emails of the other students, you know. So I believe Tariq is an amazing student. He created a community for you guys. With Tariq, go do whatever you want. Well, yes. Well, when it comes to the grouping, as you saw, you can join any group, and if the partner is comfortable with that, he will stay with the group. If not, he will leave it. So after that, you need to communicate with your partner. How are you going to communicate with your partner? When the grouping becomes permanent, I will enable direct chat between the groups, okay? The attendance for the review session, okay, 9:30, I'm bringing you, come on, at 9:30, do you think I'm gonna take attendance? However, if I call you on a scheduled time, yes, I will take attendance. Now, the reason I moved it to 9:30, there is multiple reasons. There are a lot of students who are registered in my course who already have conflicts with other courses. Okay, so as you saw, I'm providing you with the lectures. You can watch it at your own time. And by the way, please watch the lectures with a playback speed with 1.25 because I made it slow a bit in order to people from the SAS can understand it. Now, the live session, the way that I'm doing it is to go over the module to make sure that you did understand the concepts and all the objectives have been delivered effectively. If you don't like it, simply don't attend. And at the same time, what you can do is you can post the questions that you want me to cover it at the review session on Brightspace, and I'm gonna go over it. I believe like 2 students, they already posted that. Thanks a lot for them, okay? Yes, go ahead, Rawan. You can ask about the lab. You want me to unmute you? Okay, then go ahead. Oh, yes, yes. Okay, Rowan, this lab is meant to cover materials from module 2. So what you can do is you can simply at lab 1, what I already advised the TAs, if you already implement the circuit successfully, as well as included the simulation results and go over the objectives. And guys, if you want to get the objectives, you can find it on the YouTube channel of Ala. And explain it, you will get the full mark. Now, starting from lab 1, you will understand what do I mean by the truth table, okay? So I will be more lenient when it comes to lab 0, okay? So the truth table it's a table that shows all possible inputs with the output, okay? You don't need to understand it now. However, you're gonna understand it 100% at the end of module 2. No problem, Rawan. Okay, guys, can you see my screen? Perfect. Okay, perfect. Okay. So, so before I proceed, I just want to go over something, and it's very straightforward. Now, suppose that I'm a guy and I saw one of you, he loves the Japanese animation. I'm a guy who wants to watch the animation and enjoy it. So I have to learn Japanese. Is that true? The answer for sure will be true. So basically, and I love, yeah, the Midway. Can you change your name? Keep the picture, I like it, but just change your name, okay? So similarly, when it comes to computers, in order to interact with the computers, we need to understand their language. Those languages are simply the binary, because at the end of the day, even computers is still an electrical circuit that only understand high and low. So imagine that you're a guy who want to send an SOS using like a light bulb. So you will flash, okay? Each pattern has a meaning. That's why we understand binary, okay? Now, because we did understand binary at the lectures, we noticed there is multiple numerical systems. One of the numerical systems that we are using is the decimal one that we learned in elementary school, okay? At that system, there is something called the base. The base will show you how many possible digits you can have at a single space. So in the decimal system, we will have digits from 0 to 9. When it comes to the binary has a base of 2. Why? Because it needs to symbolize the way that electronics works. You know, as I told you before, a transistor can be either conducting, which is 1, or not conducting, which is 0. Okay? So basically, each digit in binary is represented by something called a bit. That bit can be either 0 or 1. If we have 2 bits, we can have up to 4 possibilities, from 0 to 3. If we have 3, we can have up to 8 possibilities, from 0 to 7, and so on. So the growth system depends on the number of bits that you have, okay? And it can be modeled in an exponential way, okay? So like here, if I have this, This is the number of bits. Okay, let me admit this, dude. I have the number of bits, and it's gonna be an exponential. So basically, if I have 7 bits, if I have 7 bits, that means I can have 2 to the power 7, which means I can have 128 possibilities. Okay, so let me delete this. All right. Okay, so one of the possible questions that I might ask you is, I want you to determine, that's something different than what I've covered on the YouTube lectures. I want you to determine the base. I give you something, some equation, and I want you to determine the base. Now, 20 over 3 equals 6. Does that make any sense to you? The answer is absolutely not. No, because 20 over 3 is not equal to 6 in the decimal system, in the numerical system that we have learned all of our life. So how can we determine the base? What we have to do is we have to use the polynomial notation. Therefore, for A here, so the 20 can be represented using the polynomial notation by showing the base and multiply it by the coefficient, and each time weighting the base to some power. So I have a 20. How can I represent the 20 knowing that I don't know the base? Okay, so it's 2 multiplied by the base to power 1 plus 0 multiplied by the base to power 0 over 3 multiplied by the base to power 0, which is equal to 6 multiplied by the base to power 0. Okay? So what does that mean? That means I will have 2b plus 0 over 3 equal to 6. Okay, can you solve this? This is like a 1-degree equation. So 2b over 3 equal to 6. That means what I have to do, multiply this by 3, multiply this by 3. So 2b will be equal to 6 multiplied by 3 is equal to 18. Okay, so b will equal to 9. So those numbers, for that equation to make sense, those number has to be belonging to the base 9. Okay, is that clear? I hope this is clear. Okay, so let's move on for the another example that we have. I have a 12 plus 24 equal to 40. Okay, now like it's either I'm drunk or there's something wrong. If I add 24 to 12, does it equal to 40? Oh, the answer is definitely no. I'm not drunk. However, those number belongs to a base that's different than the decimal one. So how can we get it? So we have, at the end of the day, this 12 can be represented by what? The 12 can be represented by b plus 2 as well as the 24 can be represented using the polynomial notation by 2b plus 4. And at this, on the other hand, the 40 can be represented by 4 multiplied by b to power 1. Yeah? Okay? So how can, what should I do? I will have 3b plus 6 equal to 4b. So b will be equal to 6. So for that equation to make sense, b has to be, or those number has to belong to a base 6. So at base 6, just like to be clear, at base 6, the numbers will start from 0, 1, 2, 3, 4, 5. And after that, if you need to represent 6, you have to move to the another digits. Okay? All right. So the last one is a very interesting example, because okay, let's leave all the questions to the end of the session, okay? Because I'm using my service book here for you to write, like for me to write properly, and I'm using 2 different Zoom accounts. So if I have 12 multiplied by 13 equal to 201. So how can I represent them using the polynomial notation? So the 12, how can can be rewritten by what? By saying that I have the base, which is 12, can be written by 1 multiplied by the base to power 1 plus 2, and 13 can be written multiplied by, the 13 can be written by the base to the power 1 multiplied by 1 plus 3, because the 3 is multiplied here to the base of 0, and the base of 0 all the time will give you 1, okay? That is equal to, so this number and this number and this number. Okay, so this number here, it's the coefficient is equal to 2 multiplied to the base to the power 2. Okay, plus the base plus 1. Okay, so b plus 2 as well as b plus 3 is equal to 2 to the base to the power 2 plus the base plus 1. Okay, so if I solve this second polynomial equation, I should get the base equal to 5. All right. Okay, that is for the first questions in our review session. Now let me move to question 2, or question 2 in my tab. Okay, now I have this equation, and I'm telling you that the solution for this equation equal to 4 and 5. Now, if you apply those in the decimal, those are not the root of this quadratic equation. So how can I solve that? How can I get the base? So what I have to do, guys, here, I have to rewrite that equation in the unknown base and make it equal to the reference point that I have, which is what? Which is the decimal, and then solve it and then get the base. In other words, so given that I'm giving you what are the roots, so what you can do is you can say, because those are the roots, I can say x minus 4 multiplied by x minus 5 is equal to 0, because those are the roots. Okay, so this, if I multiply it, this will be x to the power 2 plus if I multiply this is x to power 2 minus now here minus 5 of x, then minus 4 of x, so I will get minus 9x, then plus 20 is equal to 0. Now I have to compare it to x to power 2 minus 13x plus 32. So in other words, the 13 here, okay, the 13, the coefficient here is supposed to equal the, so how can the base x minus 13, x plus 32, so the 13 should be equal to 9, which is equal to the base plus 3. So that means the base has to be equal to 9 minus 3, which is equal to 6. All right? Okay, let me go check the chat here. How can 9 equal to 3? Rawan, how can 9 equal to 13? So this is a combination of what we did before. So 13 equal to 9. This is the base to power 1 plus 3 multiplied by the base to power 0 equal to 9. All right? So this is the base plus 3 equal to 9. So B will be equal to 6. Is that clear? Okay. So now let me go to the next questions I have on my agenda, which is this dude. Oh yeah. Okay. Now I understood what do I mean by the base. Now how can I convert from between bases? How can I get a number? How can I convert a number from the traditional decimal system that we're using to binary, to octal, to hexadecimal? And what do I mean by a PCD numbers? This is one of the questions that your colleague asked me about. Okay, so I have here the number 278.632. And this number, in order to convert it to binary, because I have first to find the binary, okay? I have to treat the integer part in a way, and I have to treat the fractional part in a different way. So how can I convert it? If you remember, I already explained that what you can use for the integer part is to divide on the new base and keep stripping. And after that, take all the remainders. So we will do it now. This process will end for sure, because at the end of the day, I can have a remainder when I divide by 2 with either 0 or 1. And like, you know, the number will end, the quantity will end. I will reach to a point I will have no longer a dividend, okay? However, when it comes to the fractional part, it's a tricky way, because you keep multiplying and stripping off the integer. And this process might go to infinity. So it's either I'm gonna ask you to do it up to 9 times and then tell me what will be the accuracy, or if we're lucky, we can get a fraction equal to half or quarter, and we can, for the half, we need just to multiply it 1 time by 2, and for the quarter, we need to multiply it 4 times, okay? So I don't wanna, like, you know, waste my time just going over this explanation, because I've already explained it. Okay, I have 2 people. Okay, next time, guys, please join on time, okay? Okay, so how can I do that? So again, as I told you, we have the integer part, 2, 7, 8, okay? So what I have to do is to keep dividing it by 2, and at the same time, I have to say generated remainder. Okay, so 278 divided by 2, what will be the answer? The answer simply is 139. This is an even number, and the remainder here is equal to 0. So 139 divided by 2, this is an odd number. This will give me like a 1 remainder for sure. 139, it's 69, and the remainder is equal to 9. Okay? So 69, again, keep dividing it by 2. Okay? What will be the answer? 34, and I have a remainder of 1. Now the 34, if I divide it by 2 again, okay, what will be the quotient there, the answer? The answer will be 34 by 34 over 2 will equal to 17, and the remainder is equal to 0. Okay, now 17 over 2, the answer is 8, the quotient is 8, and for sure the remainder is equal to 1, because 8 multiplied by 2 equal to 16. Now 8 by 2, the 8 by 2 is equal to 4, and the remainder is equal to 0. 4 divided by 2, it's 2, and the remainder is equal to 1. Now 2 divided by 2, 2 divided by 2, it's 1, and the remainder is equal to 0. Yeah. Okay, yes. I'm really sorry, yes. This is 0. Sorry, some guy called me, so I don't know. I got distracted. Now, 1 over 2, now for sure, it's gonna be, the answer should be equal to 0, the quotient, and the remainder should be equal to 1. Now, what I have to do here, I have to go from bottom to up to write my number. In other words, this is my most significant bit, okay? This is the leftmost bit. So you can say it either most significant bit MSB or leftmost bit. So this number will be rewritten as 10, the integer part, I mean, 1000101110. Okay, so the integer part of this decimal notation can be written as this in binary. Okay. Now, what about the fractional part? Now, the fractional part, as you noticed, guys. Okay, I have to admit that this guy. As you noticed, so once a remainder has formed, the integer process always terminates. Okay, for the fractional part, the fractional conversion, I have, instead of divide by the base, I have to what? I have to multiply by the base. So the multiplication can take me for infinity. Sometimes depending on the fractional part that I have, sometimes it might end, sometimes it may not. Okay, so let's stop talking and do it. Okay, so we have 0.63, and here instead that is the fractional part. And what you have to write here, instead of generated remainder, generated integer. Okay, so multiply it by 2, what will be the answer here? Okay, this is 4, 6, 12, so it will be 1.264. So what should I do is strip this. Okay, draw here. Yeah. I have to strip this dude and put it here. Then I should take the new fractional part and multiply it by 2 again. So, okay, draw, come on. Okay, so 0.264, sorry. So that is the fractional part will become here, 0.264 multiplied by 2 again, that's equal, this is 8, 12, then 4, so the answer is 0.52528. Okay. Okay. So now, did we get any integer? No. So let's strip that. Oh, okay. Come on. Strip that and take it here, and this is 0, and then move this here. 0.528. Admit. Multiply by 2 equal to 1.056. Okay, then I have draw. Come on, do it. I have to strip. I have to strip this part and generate it integer, and make it 1, and this part will become my new fraction. Okay. So this will be 0.056 multiplied by 2. That is equal to 0.12112. Okay. Just let me stop this. Okay. Then one, 1, 2. So if I strip this one, it will be 1. And then I have to take 0.112 and multiply it by 2 again, and this will be equal to 0.224. Okay. So, the video just stopped. So the question is, that's equal to 0. Now the question is, should I continue? Yeah, I'm wasting my time. So what I have to do is to agree on an accuracy. So if I told you do it, like perform the conversion for the fractional part using 5 steps. So this is 1, 2, 3, 4, and 5. You should stop here. If I told you 9, 6, no, what 9, 6? If I told you 9 times, then you have to do it again. Take this 0.224 and then multiply it by 2 again, and then the answer should be 0.448. And apparently, like, this is 0 again. And then you keep doing it. You keep doing the multiplication process. And so, as you can see, this process may not terminate. So it's usually carried on until a certain accuracy is satisfied. Okay? So what I have to do is, now for the fractional part, I have to take the binary bits from top to down. So this will be my most significant bit, and then I have to go down. So given that I have an accuracy of 60 steps at the fractional, my my fractional part, which is equal to 0.632, is equal to, starting by this one, 1, 0, 1, 1, 0, 0, and we have a decimal point, like radix point, okay? And that is 2 base 2. So in other words, both numbers, the integer, like by combining both what was the conversion results from the integer and the integer as well as the fractional part, this decimal notation can be rewritten by 1, 0. Okay, 0, I have the answer here. 0, 1, 0, 1, 1, 0.101, 0, 0, 0, 0, 1, 1. Okay, now let's suppose that, guys, I would like to convert this number. Okay, I have to admit another thing. Okay, let's suppose, guys, I would like to convert this number into an octal. So I have 2 choices, either to take the decimal one and keep dividing it by 8, because in octal, the radix or the base is equal to 8, and then get the equivalent of the integer part and get the equivalent of the fractional part, or I can use the shortcut method. So given that the octal has a base of 8, that means 8 can be represented by 2 to the power 3, which means that I can take all 3 digits, group them, and get the equivalent octal from a binary. Okay? So to do it, I have to group this. Okay, I have to start, you know, before the radix point, I have to go from right to left. And after the radix point, I have to go from left to right, okay? And this can be grouped. And this, I have nothing. So what I can do is I add a 0 here, okay? And similarly, this can be grouped, this can be grouped, and this, good, can be grouped. So what is the equivalent of this one in octal? Okay, what is the questions I have? One second. Oh yeah, you're right. I'm missing one thing. I'm missing a 0 here. Yes. So those can be grouped, those can be grouped, and those can be grouped. Now what is, okay, draw, and let's make it this in a blue. This is 4, because 1, 0, 0 equal to 4. And this is 2, and this is 6 point. That is 5, that is 0, and that is 3 to base 8. Okay? Now, what about if I want to have it in octal, in hexadecimal? So hexadecimal 16 is equal to 2 to the power 4. As such, I need to group every 4 bits to formulate the equivalent hexadecimal digit. Okay? So here, go. Those 4, and you see this one is a poor one, it has no friends in life, so I have to add 3 zeros, three fake friends. 1 0 0. So that is 1, that is 1, and that is 6. Okay, and this one I have to group them from left to right, so all these 4, and again I have a poor 1 here with no friends. So what I have to do is to add, if I add a 0 to the right at the radix point, after the radix point, that doesn't make any difference, because 0.5 half can be represented by 0.5, 0.50, 0.500, and nothing. In life, it still has the same weight, okay? So those four, and then this dude needs friends. So 3 friends for this dude, okay? So that is 1010. That's equal in binary 10, because this is 8 and this is 2. So 8 plus 2 is equal to 10. In hexadecimal, we don't have 10, because 10 requires 2 digits, but in hexadecimal, the base is 16. So we can have up to 15 possibilities with one single digit. So after 10, after 9 in hexadecimal, 10 will be represented by the alphabet letters, the first alphabet letters, which is A, and that is simply 1. And now this is the interesting part. This will become not 1. This will equal to 8. Okay, and here I wrote A instead of 1. So in other words, this hexadecimal, this decimal part can be expressed in hexadecimal by 1116.A118 to the base 16, or you can base H here, right? Or you can do a $sign. It's still the same. Okay. Okay. Now the BCD number. Why do I need BCD, guys? BCD is referring to binary coded decimal. Okay. So what does that mean? That means, you see this equivalent binary representation? I will not give a shit about that. I'm sorry to say. I will go to the decimal itself, and then convert each digit using a binary representation. So this is in binary. Don't look at it at all. So you go to this one, how the two can be represented in decimal, how the two can be represented in binary by using 4-bit, 0, 0, 1, 0. How the 7 can be represented in binary using 0, 1, 1, 1. How the 8 can be represented in a 4-bit binary representation, 1, 0, 0, 0. Okay, point. How the 6 can be represented using 4-bit representation, 6, 0, 1, 1, 0. How the 3 can be represented 0, 1, 1, no, 0, 0, 1, 1. And how the 2 can be represented again 0, 0, 1, 0. This is the equivalent BCD. So this is right away, it's equal to 2. This is right away is equal to 7. This is right away is equal to 8. And this is right away is equal to 6. And this is right away is equal to 3. And this is right away is equal to 2. So this for sure is not equivalent to the binary that I got it here. Okay. So why do I use BCD? Because sometimes, you know, I want to check the computer that I'm sending you a binary representation, but at the same time, it's just a decimal notation. Okay. All right. Okay, this I already gave you the solution now. For this questions, and this questions has been asked with one of your colleagues. So what are the difference between the signed and the unsigned numbers? Okay, so computer does not understand the minus state. So we as a human can understand if a number is in the minus format or if a number is at the positive format. But the human can understand either on, off, okay? So in binary is 1 or 0. So how can we find the solution to tell the computer or the digital circuit that we have that I'm sending, let me admit this, student. Okay, I'm sending a negative representation. So the best practice indicate that I should use the most significant bit of any binary representation to indicate the sign bit. Okay, and if, like here, let me give you an example here. If I have 0, okay, 1, 1, okay, and I have here 1, 1, 1. So using the unsigned notation, we know for sure that is 3 represented in a 3-bit representation, and this is 7. Okay, but using the signed representation, it's a different story. This is still plus 3, while this one is minus 7. Okay, so if we add, this is minus 7 in what, guys? This is minus 7 in the 10 minus 3 equal to 7. So that is in the 1's complement. It's not on the 2's complement. Okay. So basically, if I add those numbers, let's suppose that I want to add them. This is 0, and this is 1. This is 1, 1, and those are 0 and 1. So I'm getting 2. So that doesn't make any sense. So 3 minus 7 equal to 2. Does that make any sense to you? That's what we're gonna cover on the Next question. So that's why you have to stick with the specification itself. So is the number being represented in signed notation or in the unsigned? If it's at the unsigned, look at this. If it's at the unsigned, and I'll do that, it's 7, and that is equal to, that is 7, and that is 3. So this is 0 and 1, 1 and 1, and that is 0 and 1. So that is equal to 10. And it makes much sense when I do the addition here, because 3 plus 7 is equal to 10. So let's go back. I don't want to divert you from the main goal of this questions. So if you go here, okay, here, and since though to represent any number in the negative notation, you can use either the magnitude sign, the magnitude, the sign magnitude notation, and this is not recommended at all because it will induce two zeros, one plus 0, one positive 0, and one negative 0, and that doesn't make any sense in any numerical system, as well as the ones complement notation. And the ones complement notation is okay, but still has its own problem. The appropriate model to represent the signed number in binary is the 2's complement. Okay, so all my questions, the one that will require a step-by-step answers, will be based on a 2's complement numbering. Okay, so let's go back and look at this example again. So basically, what does that mean? That means I have this number. I have 0, 1, 1, 1, and then how many zeros? 0, 0, 0, 0. Okay, that means this number, I will look at the most significant bit here, which is equal to 0. 0 means positive. Okay, so what does that mean? I can get this number by doing the direct polynomial conversion. So what is this? Is 0, 1, 2, 3, 4, 5, 6. So 2 to power 6 plus 2 to power 5 plus 2 to power 4. Okay. That's equal to 112. Okay. Now let's forget about this, the other one, because it's still the same. Okay, it's still the same. We are taking this, and this is indicating 0, indicating a positive. Now let's take a look on this dude here. Okay, so I have 1, 1, 0, 1, 1, 0, 0, 1. Okay, now by grabbing the most significant bit here, which is 1, so I know for sure that's a negative. This is a negative number. So how can I get the actual number in binary, the magnitude in binary? How can I get that? Okay, so I have to convert this number back to I have to apply the 2's complement again, because negating the negation will equal to plus. So to do so, you keep this one and you start flipping all the others. 1, 1, 0, 0, and 1, 0, 0. Okay, so we have 7 plus 0, 0, 1, 2, 3, 4, and 5, plus 32, because 2 to the power 5, which is equal to 32, that is equal to 39. Okay? So the magnitude of this number is 39, and it is represented in minus, in negative. We know for sure it's in negative. Okay? So why do we need this hassle? Why do we need to learn about negative, signed, unsigned? Because in digital electronics, we cannot do the subtraction using the borrowing method we learned in elementary school. Everything has to be done using another, okay? And converting the number into its complement will help us mitigate the issues from designing another and a subtractor at the same time. We can perform addition and subtraction using the same digital circuit, as long as we're telling that circuit that those numbers are, or we're telling the engineer who's working with that circuit to represent the number using assigned to its complement format. Okay? Okay, lastly, now I want, now this questions has been covered like on the lectures. However, okay, he's joining. However, I want to do it again with you guys because the student asked me twice, and I don't want to waste I don't want to keep writing and replying back and forth. So let's suppose that I have a subtraction. I have an arithmetic operation that I would like to perform it in binary here. And this arithmetic operation is apparently the subtraction. Now, as you can see in the questions, I asked you using signs tools complement arithmetic. Okay? What does that mean? That means that the most significant bit always will indicate the sign of that number in binary. If I told you using unsigned tools complement arithmetic, we don't care about the most significant bit, okay? Now, so 185 base 10, okay. Okay, I will give you like one minute break because I got tired. Okay. Now, I just remember something, an important thing that I would like to discuss it with you, which is the number of bits to represent each number, the number of digits to represent each number matters when it comes to digital electronics, okay? So have you ever asked yourself what is the difference between a 64-bit Windows or a 32-bit Windows? Or why your iPhone 11 is so quick? Why? So, okay, you know, go user, I'm not admitting you, remove, go. I want your real name. So what is the difference? The difference, guys, those numbers simply indicate the architecture at which the CPU is designed. So back in the day, all the processors, all the CPU used the 32-bit architecture. And why this architecture sucks, sorry. Why? Because if you're saying that your CPU is built on a 32-bit architecture, that means the maximum addressable memory, all the instruction in the CPU will be executed in a binary notation from 0 up to 31. That means how many possible combination you will have. This is equal to 2 to the power 32. And 2 to the power 32 means that your RAM, your random access memory, will be limited to something equivalent to 4 gigabytes. Okay? Whereas the new iPhone, the new Intel and AMD CPUs are using now the 64-bit architecture. So 64-bit architecture means that your instructions will be formulated in a binary notation from using digits from 0 to 63. That means your CPU can handle a memory up to 2 to the power 64. And this is, you know how much this is in byte? This is 16 billion gigabytes. So that's why we're moving to this, okay? Now, away from that, what I have to do is, and I have, what I have to emphasize here, that the number of bits matters, okay? Why the number of bits matters? I have here an example, please let me. Okay, let's suppose that I have 17 and 16, and I want to do just an addition to them using a 6-bit representation. So how the 17 is represented using 6-bit, 0, 1, 0, 0, 0, that is 0, and you know, now we have to add 1 because after the 16, and the 16 is 0, 1, 0, 0, 0, and 0, okay? Yeah, because this is 2 to the power 4, and this is 16, and this is 2 to the power 4 plus 1, this is equal to 17. Now, if I do the addition here, that is 1, 0, 0, 0, and you know, 0, and this is another 1 and 1, so this is 0, and what? And I have a carry out, okay, equal to 1 here. So that is in 3, that is in 3. So this carry out, when I do any addition, I always was discarded, you know. But what will happen here if I discard it? 16 plus 17 plus 16 is equal to 1. Does that make sense to you? No, that doesn't make any sense. But this is in reality what's going on. The number of bits that used to represent a number matters. Okay? So in this case, this addition is giving me an invalid result because I'm getting something called an overflow. What does overflow means? You're exceeding the number of digits allowed to do your to represent your number. So how to solve that? Simply by using a 7-bit representation. So we have to add 0 here, and we have to add 0 here. So what will happen here? This 1 will not be a carry out anymore, and I can keep it. So this answer will be equal to 31. Okay. So an overflow happens when you add 2 positive numbers, and then the answer cannot be represented because of a space limitation, or the resultant answer can be negative. How to detect the overflow, that's what we will cover in chapter 3. It's outside the scope of today's lecture. Okay, as well as, yeah, an overflow can happen in the 2's complement notation by adding 2 negative numbers and the result is positive. Okay, so how to detect the overflow, I will cover it on module 3. Okay, so let's not stick pay attention to it now. Okay, so why did I explain that? If I do a subtraction and I want to make sure that everything is fine with me, I will not go to a direction where I get an overflow or where I will get a less or insufficient bit to represent my number. I will always look at my bigger number here. My bigger number is 230. So the number to the number of digits used to perform this subtraction will be based on the bigger number that I have. Okay. So 230, if I would like 230 to be converted to decimal, to binary, how can I do it? Using the method that I've shown you. You have to keep dividing it by 2 and then take all the remainders. So the 230 requires 8-bit to be represented. Okay, so 230 in magnitude, what will be the 230? It is 1 0 1 1 1 and then 0 0 1. Okay, like if you add them, this is 1, this is 2 this is 8, and this is 16, 32, and 64. If I'm not mistaken, yeah, that is, yes. So you add them together, they will give you 230. So they the 230 requires 8-bit to be represented. And since I asked you to do it using sign, you should add an extra bit. Okay. So even if you want to subtract 1 from the 230, the other operand, the one has to be represented using 9-bit representation. So we'll not get to any problem. Okay. So this is 230 plus 230. Okay, so that is 230. Okay, so the plus 230, is equal to 0 at the beginning and the magnitude itself, 0 1 1 1 1 0 0 1. Okay, and if I would like to represent the minus 230, what should I take? Just the 2 complements of my number here, which is 0 1 0 1 1 1 0 0 1. That is equal. How to do that? How to get the 2's complement directly? You go from, examine your number from left to right, and you keep the first one you encounter, and then you start flipping. So that is, I will keep this one here, and this one will become 1. This will become 1. This will become 1. Okay, let me do it underneath so you can understand, and in a different color. This first one will come here, and after that I have to flip them. So this will become 1 1 zeros, and this will become 1 0 and 1. So as you can see, the most significant bit is 1, indicating that this number is negative. That's minus 230. What about the 185? Now the 185 might not require 8-bit to be represented, but I have to write it in I have to write it. Actually, I made a mistake here, a big mistake here. Yes. I have copied the conversion of 230 in a wrong representation. So the 230 is represented by 0 1 1 1 0 1 1 0, 0, 1, 1, 1, 0, 1, 1, 0. This is the 230 plus 230. So the 85, the plus 85 will be represented by 0, 1, 0, 1, then 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, and 1. Okay? Now, if I want to get the 2's complement of the 230 to represent the minus 230, that is equal to, now, for this one, you go from left to right, and so I'm going to keep just this one and start flipping. So it will be 0, 1, then 0. This one will become 0, 1, then 0, 0, 0, and this one. Okay, that is the minus 230. And for the 85, if no, okay, for the minus 185, what should I do is to take the 2's complement of to represent the to represent the negative representation of the 185. So as I did before and delete it, so this will be like, keep this one and flipping those 1, 1, 0, 0, then 0, 1, 0, 0, 1, 1, and 0. Okay, so that is the minus 185. So if I would like to, now if I would like to do any operation, now all of them can be done in addition. In other words, if I want to do this, 230 minus 185, what should I do? I should, okay, this is in blue, okay? What should I do? I should take the plus here and then simply add it to, and simply add it to the negative here. That's it. Okay. And this is 1. Okay, flipping it. So 1, then flip this one, 1, 1, 0, 0, 0, then 1. This is 0, and this is 1. Okay. So how to do it? 0, 1, 1, 1, then 0, 1, 1, 0. Okay. Plus 1, then 1, then 1, and then 0, 0, 0, then 1, 0, 1. Okay, am I missing one number here? Yeah, I'm missing this dude. So that means here I have another one. Okay. So 0, 1, 1, 0, 0, 1, 1, 1, and 0 plus. So it will be 1, 1, 1, 0, 0, and 0, and 1, 0, 1. Okay, so do like a direct addition here. So the direct addition, that is 1, that is 0, that is 1, 1. Okay, this, and then this is 0, 1, then 0, 0, and 0, 0, and 0, and 1. Okay, so what we have to do is, again, 0, 1, it's 1, 1 and 1, it's 0, and we have a carry of 1. So now I have a 3, so I will put 1, and a carry of 1. This will give me just 1. This will give me 0. This is 1, 0, and this is 1, 1, 0. This will, yes, this will give me like 2, and this will give me 2 again, and this will give me 2 again. So then this will be considered like 1 here. I have it here, and this one will be considered a carry out. So this carry out in 2's complement, we will always what? Neglect it. And this will be my final answer. Since I know for a fact that 230 is bigger than 185, the result is positive, okay? So if I got a result, if I do the opposite, if I subtracted 185 from 230, the result will be negative. So what I have to do is to take the 2's complement in order to represent it, okay? So that is will be equivalent to plus 45, okay? Okay, now let me stop sharing from this machine and go to my main one. And see your answers, see whatever you want. Okay, now guys, I want you to raise your hand if you have any questions, if you wrote anything, because I missed most of your chat. Okay. Or I'm gonna unmute you, but be considerate, please. You know, make sure that you don't have any noise and don't talk while the other is talking. You wanna go to the space? So who has a question, guys? Who has any question?
Hello?
Yes.
I had a question, if that's all right.
Go ahead.
So for the last question that we just did, do we always take out the carryover? Like, let's say the answer is negative, because in this case it was positive 45. If the answer was negative and we had 1, you know, and then we ignored that, is the answer okay?
Okay. Can you raise your hand? Can you raise your hand, because I will just unmute you. I don't know who asked me that question, so I want him to raise his hand so I can go and unmute him. Oh, yeah, okay, you don't know. Yes, thank you. I am? Okay, unmute.
Yeah, thank you. First prof to get my name right.
Yeah.
So yeah, I was thinking if we always
no, I am. Look, buddy. So you know, the largest number will determine how many bits I will need to represent. I will need to do my arithmetics. Yes.
Mm-hmm.
So the carry out is, you know, let's suppose that I have 4 bits. You know, both my operands are represented by 4 bits, and then I got an answer with 5 bits. That 5th one is considered the carry out. Okay.
Okay.
So that's the one that needs to be discarded. If the answer is, you know, it is in 4-bit and like the most significant digit is considered 1, is 1, you know, at your answer, that means your answer is in negative. So what you have to do is to take the 2's complement to get the right magnitude. That's it.
Okay, I see. All right. Thank you.
Okay. Okay. So anybody has another question? Oh, can you? Okay, lower. Where's Muhammad? Can you raise your hand again? I'm really sorry. I did not see you. Yes. Okay, go ahead.
Hello, Professor. I just have a question about converting to the. So on the slide where we had to convert into the octal and the hexadecimal, we had to convert also to the BCM?
No, this is BCD. BCD. The binary coded decimal is, I just want to be catchy with you.
Okay, so BCD.
The BCD, let me share it somewhere. Okay. Can you give me just a second so I will share it on my big machine here?
Sure.
What is that number? Yeah. Share. Let's do share. Can you see it here?
Yeah.
Okay, so you know, when we did the conversion to binary, that was the result, yes?
Yes.
Using the division and taking the remainder, as well as stripping off the integer from the fraction, yes?
Mm-hmm.
So if you want to get the hexadecimal from the binary notation, you group the 4. Okay?
Yes.
However, for the BCD, you don't look at the binary notation anymore. Otherwise, you will get an error. If you're gonna group this as 4, and then this will not give you what you want. Okay?
Yeah.
So if I group this for 0, 1, 1, 0, this is 6. So is 6 representing 8 here?
No.
No. So how to get the BCD is to look at the decimal again and convert each digit into a binary notation. That's it, using a 4-bit representation. So the 2 here is representing by, come on, go ahead.
Oh, the 2.
Yeah, the 2
0,
will be represented here as, yes, as this is, and this is even wrong. Okay, by this. Okay, 0, 0, 0, 1, 0. That is the 2. The 7 by here, adding a 0 as well. Okay, and this is 8. You see that?
Yes.
And so on. That's it. So you go to each digit and write the equivalent binary notation using 4-bit. You don't look at the binary anymore. Okay?
I also have another question. So 4 bits can represent up to 15, right?
Yes.
Okay. So for example, if we have 215, we represent 2 as 0010. Do we represent
215?
Yes.
Okay, just give me a second here. Let me stop this. I will explain how to get leave. Okay, I believe I can do something using this. I don't know. This is, yeah, just give me a second. I'm gonna use my graphical tablet to write. Yeah. Okay, now excuse my writing here. It's gonna be bad because it's something similar to mouse. So if you have 4 digits, yes?
Yes.
Oh, no. Yes. If you have 4 digits, so digits in binary, 4 bits, you mean? So
Yeah.
that is 2 to the power 4. That is equal to 16. So you can represent numbers from 0 to 16, to 15. The first one will be 4 zeros, and the last one will be 4 ones. Yeah? So what is the question again?
When we want to represent 215 in BCD, do we consider 15 as
Yeah, okay.
111?
Okay, let's suppose that I want to represent 16 in BCD, okay? This is 16 in decimal. I want to represent it in BCD. How? So am I gonna write 111 10000? No.
No.
So the 1 can be represented using 4-bit by zeros. Sorry, 3 zeros. Add 1. And the 6 can be represented by 0, 1, 1, 0. That is 16 in BCD.
Okay, and what about the number we can represent in 4 bits? For example, 15
There's no numbers in BCD. Dude, BCD. Look at the decimal. The decimal will end up to 9. Yes, the numbers. Yeah, the decimal represent digits that represent numbers in a single digits that can range from 0 to 9. In 10, there is nothing in decimal. It's the same number but with a different digit. Okay?
Okay, I got it.
Yeah, you got it? So in decimal, in our decimal, yes, it's in the base of 10, but it only can contain numbers from 0 to 9. If we want to write 10, what it's a new, like, you know, we just finished the first range and we're going to start another range. So that is equal, this is equal to 1 multiplied by 10, the base to power 1, plus 0 multiplied by what? 10 to the power 0. This will give you 0 and this will give you 10. As simple as that.
Okay. Thank
Better?
you.
Okay, let me go back and stop sharing. Okay, who has a question? Okay, Valerie, go ahead.
Hi, I was just wondering if there were any like exercises or something that we can find to work on these sort of questions.
Yeah, let me tell you something. Your assignment will be posted this weekend. And you're gonna you probably will hate me, okay?
Great. Perfect. Great.
Okay. As well as the DGD will take place this week because we finished the module. So Ala will present your first DGD. It will be something similar to the recording. And if you have any question about what he explained, you have to use the discussion tool as well as email him so he can go live. Okay?
Okay.
Okay. So any other question, guys?
Thanks.
You're welcome. Who has a question here? Okay. Go ahead. I'm so sorry to, like, I cannot pronounce your name properly, but I'm gonna go with XU Feng. Unmute.
Hello.
Yes. Go ahead.
My question is, what is 0 minus 1?
0 minus 1 thing.
Yeah.
0 minus 1 is equal to what? It's equal
Is it
to 1, but 1 is negative. So 0 minus 1 can be done by borrowing, you know, or just simply saying it's 1.
Is it a positive 1 or negative 1?
What,
0 minus 1 in base of 2.
0 minus, okay, where's, let's go here and do the 0 minus 1. So 0 minus 1. Actually, the answer, according to us as a human, it should be minus 1, yeah?
Yes.
But computer does not understand minus. So what you have to do is you have to borrow from anywhere, and this will become 2, and the answer should be 1. Okay, and this one because it will be the most significant bit at the same time, you know, because it's that single digit, and this will represent it's a -1. Okay.
Oh, yeah. Okay. Okay. Understand. Yeah. Thank
Yeah.
you.
You're welcome.
Hello, sir.
Yeah, Muhammad, go ahead. Okay, Muhammad, you have a question? I try to unmute you. I can't. Okay, I'm gonna go with Tanting. If I am.
Yeah. Hello, sir.
Yes, go ahead.
Yeah, I just wanted to know if we still have a lab on Wednesday. Like, do we
No,
have
no,
that?
okay. You know, guys, I sometimes, you know, I will lose my mind because even like I'm explaining everything on Brightspace and I'm still getting information. So apparently, like the way that I'm doing this course is using the asynchronous mode, at which I'm providing you with the lecture, watch it at your own time, anytime, and then you can ask using Brightspace. So any information you need to discuss it with me, if you can give me just 1 second here.
All right.
Okay, let's take it here and let's go as a student. Okay, so this is what you're gonna see it exactly. So let's share this screen with you. Can you see it? The bright split? Yes. So look at the bright split. Lab schedules and logistics. What will be the starting week at lab 1? May 25.
Yeah, I'm talking of lab 0 because it happened at a time when I was like I had a different class then, so I couldn't attend it.
Yeah, but I did not ask you to attend it. You can watch it.
Oh, all right, sir.
Okay. So listen, you know, I will, and this is for everybody. I have no problem enforcing synchronous mode, at which I'm gonna go live on the scheduled time, but I will take attendance. Do you want that?
No.
Okay. So okay, so it's not just for you, for everybody here. So so those are the timing at which your lab will take place, at which you will receive the video from my TA, as well as the manual to do the lab. And if you have any question all along the week, you can consult the this table, and you can Skype any one of them according to the time that you like.
All right, sir.
And if, you know, let's suppose that you're busy at this time, send Ala an email, shoot him an email, he will schedule a time for you.
All right, sir. Thank you very much.
Okay, so
Yes,
similarly, the DGD, okay? So
Yeah.
we finished module 1. So you will receive a video May 17, which is next week. You will find the video on the DGD tab, on the tutorial tab, okay?
Okay, sir. Thank you.
You're welcome. So who has any question, guys? Okay, Muhammad, I try to unmute you, but it seems you don't have any question. If you have any question, you can raise your hand. You have 5 minutes to do so. Otherwise, I'm gonna end the session. No, okay, again. Okay, for lab 0, it's 1 lab report per group. Okay, you know, guys, you know what? Just do the experiment, follow the steps, do something similar to the cover page that I gave you. Okay, let me share it here. Share screen. Go here. Okay, here. Oh, here, labs. Here, lab report format. You know. Okay, do something similar to it. You know, circuit diagram. I already gave you the circuit diagram, but just do it again in Quartz and have it. You know, show me the experiment results by going over the waveform and explaining it. you know, discussed any challenges that you have, you know, like those who are on Mac, they, you know, they bomb the discussion with their with that challenge. So tell me that it was you had a problem using the Altera on Mac. I have to install Parallel. I have to pay money. I'm a poor student, you know, to buy the Parallel. So just let me know about that. That's it, and then you will get the full mark. I don't know sometimes why you're making it hard on yourself. Okay, from lab 1, you will understand what do I mean by a truth table, how to analyze it, how to get the theoretical answer of any Boolean function, and is it matching whatever you have on the simulation, and then you will follow that format properly. Okay. Huh? Okay.
Hello?
Yes. Yes.
Oh, yeah. So this is more of a general question about the class, but so far in module 1, I've noticed like a pattern of like where we see a way to do something, like let's say subtraction, and then like a shortcut to do the same thing. So then like subtraction with the 2's complement, for example. So I was wondering, in these situations, should we know both methods, or is it sufficient to just know the shortcut?
Just the complement method is
Mm-hmm.
the one requested at any exam, you know.
Okay.
Yeah.
Perfect.
The borrowing is I have to give you a method that matches whatever you learned before, you
Yeah.
know,
Mm-hmm.
and it's still the same, you know, the same principle. But what is new is how the computer is performing the subtraction,
Mm-hmm.
which is using the complement. By the way, do you know what's the difference between a human and a computer?
Well, I couldn't tell you exactly.
So we as a human, we can think, decide. Computer can just perform things,
Mm-hmm.
you know?
Yeah, they have to go through the program and that's it.
Exactly. So you have to instruct the computer what to do, because at the end of the day, it's just like a transistor. When you say nanotechnology, that means how many millions of transistor is on the chip, you know?
Mm-hmm.
So that is the big difference between human and computer. Until these days where they're pushing for the AI as well as the machine learning, where can machine decides, you know, but still, it's still, there is no AI, it's machine learning. Machine learning means you give multiple rules and the machine can decide which data is important to you, okay?
Mm-hmm. That's pretty cool. Thank you.
Okay, guys, so I really have, we have no more questions. And yes, this is just an important note to all of you. The recording of this lecture will be posted on Brightspace. So anybody who missed it, he can watch it. I wish you a very wonderful night. Okay, oh, Catherine Chen, as shown in lecture subtract. Okay, why does it equal to? Oh, you have to try it. I've explained it. You know, I've explained it, Catherine. Okay. If you really don't want, like, if you don't have any more questions and you don't want to raise your hand, you can leave. Other than that, I'm gonna end the chat very soon. Yes, go ahead. Go ahead. Go ahead. Go ahead. Good night. Go ahead. Either raise your hand or what? Or type. Okay, raise your hand. I can't see you. Yes. Go ahead.
Hello.
Yes.
Yeah. I have a question about the diminished radius complement and the normal complement. So in your lecture, you said the diminished radius complement is easier to calculate for human, but when we build the computer system, do we always use the radius complement because it costs less hardware? So which means it will cost less. But the human, we as a human, we always use the diminished radius complement to calculate. Is this right?
Yeah, that's somewhat right, you know. So the most accurate complement is the radix one, because because you simply don't need to worry about the carry. You don't need to do about inducing an invalid number while you're complementing. If you watched my video, you will see that the ones complement induced a -0. Does that sounds good to you? No.
So which mean in computer the radius complement has one more last step to do. So which mean it will cost less hardware.
Exactly.
And the last one memory in the CPU, is that right?
Listen, you know what? Like, can we leave that to chapter 3? I will show you the cost in terms of a mathematical function, and you will understand it. You know, like you're somewhat right, because at the end, if you noticed, when we use the diminished radix complement, like let's say the ones complement, at the end we need to add the carry. We'll not neglect it. Yeah.
Yes. Yeah.
So that means you have to do you have to add another somewhere, you know, at the end, you know. So that means inducing an extra hardware. Okay.
Yeah.
Okay. Okay, have a nice night, everybody. Why does one complement exist, though? Because some guy invented it, and we have to learn it. Okay? Happy weekend. Have a nice day. Bye-bye.